All right, let's just jump right in. We're about to question something so fundamental, it sounds a little crazy. I know what you're thinking when you see a title like that. But what if one of the biggest rules in all of physics isn't what we've been told? What if it's all a huge misunderstanding about how our reality actually works? You know the story. We've all been taught it. We picture these little photons, these tiny bullets of light, just zipping across the universe. We think of them as these heroic travelers crossing an endless cosmic road. It's a simple, neat picture. But what if that picture is completely, totally wrong? What if it's just a convenient story we tell ourselves because it's what our senses can understand? The truth, as we're about to explore, might be way stranger and a lot more digital. Okay, so here's the absolute core of the idea. C, the speed of light, isn't the speed of a thing moving. It's a fundamental property of the system we're in. Forget the speed limit on a highway. Think of it like the bandwidth of your Wi-Fi. It's the absolute maximum rate that any information can move through the grid of reality. It is literally the universe's refresh rate. So, how did we get this so wrong for so long? Well, we've got to go back in time. It wasn't some grand conspiracy, of course. It was just a misinterpretation of the clues we had. Let's walk through the steps that let us mistake a system spec for a traveler's speed. So it all starts with Newton, right? His physics made perfect sense. If you're on a train and you throw a ball, the train speed and the ball's speed add up. Simple. So for a long time, everyone figured light must work the same way, moving through some invisible cosmic goo they call the ether. But then in 1887, an experiment designed to find this ether found nothing. It totally failed. This broke physics. So Einstein comes along and says, okay, forget the ether. Let's just accept that the speed of light is always the same no matter what. He made it a fundamental rule, but he never really explained why. And I want you to really appreciate what a huge deal this was. They were expecting a really obvious result. The data should have shifted pretty significantly. But what they got was nothing. Zilch, a flat line. Light just refused to change its speed. Now, if you think like a programmer, that's a massive clue. When you have a value in a system that you can't change no matter what you do to it, it's not a variable. It's a hard-coded constant. It's part of the architecture. And that brings us to the whole new way of looking at this. The reason C is constant is because the universe isn't a smooth, continuous painting. It's a digital image. It's made of pixels. It has a finite resolution. So let's take a look at the spec sheet for reality's operating system. Now, look at this number. It's so small, it's basically impossible to imagine. This is the Planck length. It's the universe's tiniest possible pixel, or voxel, since we're in 3D. You literally cannot have a distance smaller than this. Space isn't continuous. It comes in these tiny, discrete chunks. And you know, if space comes in minimum-sized chunks, then time has to as well. This is the Planck time. It's the shortest possible moment. It's one tick of the universe's internal clock. It is the fundamental refresh rate of reality itself. And here it is. This is the big reveal. You take the smallest possible distance and divide it by the shortest possible time, and what do you get? You get the speed of light. See? It's not a velocity. It's just a ratio built into the fabric of the cosmos, 1 pixel per tick. Nothing can move faster than that because the system can only process a change from 1 pixel to the next in a single tick. That's the absolute limit. Okay, so once you accept this, once you see the universe as a computer, all the other weird things in physics suddenly stop being so weird. They start looking less like paradoxes and more like clever resource management. They're not bugs, they're features. Let's start with gravity. The old view is that mass bends space-time. Fine. But in this new model, mass is just a huge concentration of information. Think about what happens in a video game when there's way too much happening on screen. The frame rate drops, right? It gets laggy. That's gravity. A black hole is an area with so much information density that the local processor is struggling to keep up, and what we feel as gravity is just that slowdown. It's cosmic lag. And quantum mechanics? Oh man, it goes from being this magical, confusing mess to just being a really, really efficient rendering engine. You know, a particle isn't in a million places at once. The system just hasn't bothered to calculate its exact position yet to save on processing power. It's called lazy loading in programming. The moment we measure it, that's the wave function collapse. That's the system finally spending the energy to render the particle into a definite state, only when it absolutely has to.
And that spooky action at a distance, entanglement, it sounds like magic. But in computer science, it's not spooky at all. It's just two variables pointing to the same piece of data in memory. If you change the data, both variables update instantly, no matter how far apart they are in the program's output. The distance doesn't matter. They're linked at a deeper, structural level.
So if our universe really is a kind of computer, then it has to have specs, right? It must have limits. How much processing power does it have? What's the total storage capacity of our reality? This leads us to one of the most brain-bending concepts out there, the holographic principle. It basically says that all the information to create a 3D space, like our universe, can be stored on a 2D surface. Kind of like how a 3D movie is stored on a flat Blu-ray disc. It's a wild idea that suggests our 3D reality might just be a projection of information from some other lower dimension. And if you're still not sold, get this. This is the kicker. A physicist, S. James Gates Jr., was working on the deep equations of supersymmetry, and he found something that shouldn't be there. He found error-correcting code, the exact same kind of code web browsers use to make sure data arrives without getting corrupted. I mean, why would the laws of physics need error correction, unless reality itself is a stream of data? So here you have it, the spec sheet for reality version 1.0. All these fundamental constants we thought were separate, random numbers, they all click together perfectly as the parameters of a single computational system. We've got a max bandwidth, a clock speed, a pixel resolution, a minimum packet size for data, and even a rough estimate for the total operations the universe has ever performed. It's mind-bogglingly huge, but it's not infinite. And that, of course, leads us to the final, and frankly, kind of chilling question. If we're inside a simulated system, one with finite resources that has to manage its processing load so it doesn't crash, what happens if we, the inhabitants, create too much complexity? What happens if the computational load just gets too high? What's the ultimate fix for a system that freezes? It's a thought that takes this from a cool science idea and makes it something very, very personal.